All right, welcome to MA 103's lesson on model evaluation. And so for this lesson, I'm going to show you guys how to set up a spreadsheet and evaluate a model using a linear model from a data set that's on the course webpage. So if you go to the Block 4 tab, this Block 4 tab on the course webpage, and go down to Firearms Data, this is the data set that I'm going to use for this model. So if you want to download that and follow along, you're more than welcome to, right? And so when you download it, you'll get this website, this worksheet right here, okay? And so it's got a bunch of different factors. What I want to do is I want to model and see how does percent of the population owning guns influence the firearms deaths per 100,000. And so what I've done is I've copied these two columns of data and I've pasted them on the next page. You'll also notice that I rearranged them. So instead of firearms and percent of gun owning population, I just flipped them and put the percent of gun owning population first, because I want to know if I told you that everyone had guns, what would my model predict in terms of the firearms deaths per 100,000? Okay, and so anytime we get a data set, the first thing that we want to do is we want to plot it. And to do that, you want to select all of your data, and so you can either highlight and drag it, or if you highlight the first two, the two columns that you want, you hit Control Shift and the down arrow, it'll select everything in that column where there's no spaces, right? So if there was a space, it might get cut short, but anyways, we want to insert this scatter plot, and there it is, right? And so at first glance, this seems to indicate that as gun ownership increases, so do the deaths from firearms. And so we kind of visualize, if we're going to model a linear data set, we can kind of visualize this trend. I could draw a line in here and suggest some kind of linear model that looks like this, right? And so what we want to do is, if we're building a linear model, we know we have two parameters. My parameters are M and B. I've got a slope and I've got a y-intercept. And so as I've drawn this line, my line goes through 2 points, and I can use those 2 points to get my base estimate for slope and y-intercept. And so I've got this, I go through this first point here, which is 6.7 and 3.6. So it's this observation right here. So I'm just going to highlight it because we're going to come back to it. And it goes through this observation, 57.7 and 16. And so that observation's right here. Okay, and so I'm going to use those 2 points for my base estimate. So my slope is pretty easy, right? It's just y2 minus y1 divided by x2 minus x1. And so there's my slope. And so using that slope, I could use point slope form to find my y-intercept. And so in doing that, it's going to be my slope times the negative x value plus y. Okay, and so this says my y-intercept is 1.97, or almost 2. All right, and so now let's build our model. And so in the column, this column D here, we're going to type model. You'll also see y hat, or y with the little hat above it. That indicates that that's our predicted value. Okay, and so my model is going to be just a linear model, so it's mx times mx plus b. So here's my slope, and I'm going to reference the slope every single time, so I want to use the F4 key to make it an absolute cell reference. So it's m times my x value, which is this gun ownership rate, plus my y-intercept. And again, I'm going to use this y-intercept for every single observation, so I use the F4 key to make it an absolute cell reference. Anytime you're referencing a parameter, you want to use an absolute cell reference. All right, so there's my prediction, and I can just double-click the bottom right corner, and it's going to make a prediction for all of these values. So you'll notice that my prediction mirrors, or is exact right here for this observation and for this, and it should be, right? Because my model is a line that goes through those 2 points, so I should get those two predictions correct. The next thing that we want to do is we want to figure out how much error is in our model. The eyeball test, just looking at this, the eyeball test says our model generally follows the trend. And actually, let's delete this line. Let's plot our model. Right, so to plot our model, if we click on the plot, you'll notice this purple box and a blue box over here. We just want to grab the upper right corner of this blue box and we can drag it over, and now it's plotted. And if we wanted to get crazy, we can click on that. We can actually change this by going to Insert. We could make it a line if we wanted to. Not necessary, just thought I'd show you. Right, so there's our model. The eyeball test says it generally follows the trend. It's not a bad model in that some of our observations are above the line, some of our observations are below the line. They seem somewhat fairly evenly distributed. So all in all, it's not a bad model. But if we want to make it do an objective assessment, we need to figure out how much error is in our model. Okay, and so we're going to find the error squared actually. And so our error is equal to what did I predict, right, minus what did I observe. Okay, and so that's error, and we want to square that. So there's my squared error, and again, I'm going to do that for every observation. And that takes it down there. Okay, and so now what we're going to do is move this over and give us a little bit more room. We want to figure out the sum of the squared error. So SSE, sum of squared error, that's just equal to the sum of all of these squared error observations, right? So again, I could click and drag and highlight all this, or I could click the first value, hit Control Shift and the down key, now hit Enter. So there's my sum of squared error, 392. And so I could optimize my model right here, right? I just need to minimize the sum of squared error, but I think we ask you to also compute the coefficient of determination, the R squared value. And to do that, first we need y bar, which is the average of all of our observations, right? So that's equal to the average of all of these observations. So these are our observations right here. So the average number of deaths in any of the states is 10.78. That's the average number of firearms deaths per 100,000 people. Okay, and so to find my sum squared total, I'm going to create another column up here that says total squared. And the total squared is equal to the average minus the observation squared. Okay, and so this is straight off the formula reference card, but we're going to do y bar, and we're going to reference y bar every single time. So we use the F4 key minus the observation yi, right? And so this is the observation. It has nothing to do with our model. It's just using the observed values. And so we're going to do this, and we're going to square it, and that's my total squared for the first observation. We can double click the bottom right corner and do this for every observation now. And so my SSE, my SST, my sum of squares total, is equal to the sum of all of these observations. All right, so 746.41. And now if we use our formula reference card one more time, we can find the coefficient of determination. So R squared is equal to 1 minus the SSE, sum squared error, divided by the sum of squares total. It tells us we're at 0.47. Okay, and so this tells us that our model accounts for about 47% of the variation in the data. We want the coefficient of determination to be as high as possible, and the greatest value that it could be is 1. All right, and so the closer to 1, in some sense, it's the better model, right? Because in effect, we've reduced the amount of error in our model. And so now we can use this built-in function solver to optimize our model, right? We're going to figure out these two values that give us the best fit model. And so we can do that one of two ways. We can minimize the error in our model, or we can maximize the coefficient of determination. And so in this example, I'll go ahead and maximize our squared value. And so I click on that cell, and then I'm going to choose the solver function. And the first thing we got to do is we got to set our objective cell, and our objective is this cell right here, J11, right? Our R squared value. And what we want to do is we want to maximize that value. We want it to be as close to 1 as possible. The next thing solver asks us is by changing variable cells. There's only two things that we can change. We can change our slope, and we can change our y-intercept. So we're going to highlight those two things and hit enter. Subject to this constraint, sometimes you'll see this box checked that says make unconstrained variables non-negative. We don't want to limit our variables to being strictly positive, so we'll uncheck that box and then hit solve. And so now Solver has run, and it has changed our slope and our y-intercept, and it's also increased our r-squared value to 0.498. So there we go. We have optimized our linear model. We started out, we used two values to give us a idea of the slope and the y-intercept, and then we use Solver to find the best fit, and that's what this is. So we're going to do the same process in the coming lessons for power models, exponential models, and trig models, but every single one of them will be set up in the same fashion, where we find we get initial baseline estimates for our parameters, we build a model, we compute the error, and then we optimize our model using Solver.